All right, before we officially get started, we have an exam next week at Wednesday, right? During lab. When do you want to do the review session? Do you want to do it this coming Thursday, have the weekend to study, or would you rather do it on Tuesday right before the exam? Who votes for Thursday? Who votes for Tuesday, the week after? Let's do a poll on TV land. So I think, let's see, let's edit that.
That's the only reason I can vote. You're afraid of it's gonna be like the wrong thing.
All right, let's launch this. All right, TV land folks, go ahead if you want your review session on Thursday or the Tuesday before the exam. So go ahead and vote. So I think it's almost unanimous that, yeah, so that's 6 out of 8. And I think it was about the same percentages here. So we'll do it on Thursday. Okay. So I got to put together an exam review for Thursday. I'll get that posted and then we'll go through. Sound good? Okay. So now we're moving again more and more into design elements of control systems. And we've already talked a little bit about if we have a second order system, how do we get the second order system to respond in certain characteristics, time and all that stuff. Well, one of the things we haven't really talked about is we want the system to eventually go to a value. That's why we call it our input is our set point, right? We want it to be at 55 or 32 or whatever value it is. If the output can't get to 55 or 32, then we're going to get some sort of error, right? We have to accept the fact that there's going to be error. The problem with that is error going to be acceptable to us or not? And so what we're looking at today is looking at long-term or steady state error of our system. Oops, let's not move. So normally, at least in the process control world, we normally want things to be going to a set point that's fixed, right? We want it to be 82, 36, whatever value we want. It doesn't necessarily have to be though, right? So maybe we want something that is oscillatory, like tracking. You're trying to track a missile. Let's say if you're doing defense and you're tracking a missile in the air. Well, the distance away from you is increasing, probably at a ramp rate. Or maybe its speed is increasing. We don't necessarily know. So if we're tracking something along, we need to be able to adjust at a ramping rate. Okay. We could also do sinusoidal ones, oscillatory ones, but those we tend to not worry too much about because for the most part, you don't want something swinging back and forth necessarily. That would be very difficult to control. So let's take a look at our control system. And this is a closed loop control system. And you'll notice this has unity feedback. This is not a requirement of a system to calculate steady state error, but it usually is preferred and desired. And the reason why is this is my set point and this is my output. My error should be the difference between the set point and the output, right? So if your output can't be exactly compared against your set point, then you have to put an H block in there, right? So technically speaking, you aren't really calculating steady state error if you have an H that's not unity. It just means, it's still okay. It's still going to be okay. So technically this signal here would not be an error signal. It would be maybe a delta or a difference or something between my set point and the fed back output. So it's not a direct comparison. But if we assume, we'll try to assume, but it doesn't have to be, if H is going to be equal to 1, then we're in good shape. If H is not equal to 1, what changes? The only thing that changes is we have to include an H over here. Okay? So if H is not equal to 1, you would need to include an H here and then an H here. But for now, let's just assume that H is equal to 1 to make it easier. These two blocks are in cascade. How do I manage blocks that are in cascade? What do I need to do to them? Multiply them together, right? So this becomes GC and GP. And this is negative feedback. So remember the transfer function for a system that's in negative feedback, I'll just write TF, is the forward plus 1 over G times H. G is equal to 1, right? So here is the actual transfer function. And then I'm going to multiply that here by my value of R. Now, calculating my error, this is where the error exists. It's the difference between the input and the output. And if this is directly comparing, I can just bring that value back. So I'm going to subtract the output from the input to calculate error. Does anybody see or want to see how I got this expression here? Or does it make sense to you? How did I go from this part essentially to this? You all see it? Does anybody want me to do the work? How about I just do the work because I can do it faster. So R of S is my input. I'm just going to call it R minus C, but C is defined over here. GC, GP over 1 plus GC, GP times R. Everybody okay with that? That's the error is equal to that. Now, common denominator, right? So everything is over 1 plus GC, GP, which means I need to multiply that first R by 1 plus GC, GP, and then I subtract GC, GP times R. I can see that the R times GC, GP is going to cancel this GC, GP, R. So what I'm left with is R over 1 plus GC, GP, which is that term right there. Just a little bit of algebra to get there. Okay. Now, that's the actual E of S system. So if I want to calculate what E of T is, I can bring this back to the time domain doing partial fraction expansion and do all what I want. Well, what I'm more interested in is over time, what's going to happen, or what does my error look like? Is there a really useful tool that we've discussed in this class numerous times to get us what that error is going to be at a long period of time? MATLAB? You like that? How about final value theorem? Isn't that much faster than doing MATLAB? No? You good at it? The final value theorem, remember, is the limit as S approaches 0, E of S, got to multiply by S, right? That's all the final value theorem is. So this is going to give me a time domain response from a Laplace domain function, right? This is E of S. This is in the Laplace domain. This is in the time domain. So I'm going to apply the final value theorem to solve for that. So this is what I'm doing over here. This is the final value theorem, which says in steady state, or as t approaches infinity, I have the limit as s approaches 0, s times E of S. So I'm going to stuff that in generically over here. So my steady state error for any system is going to be equal to, what's this term again right here? What's R of S? Input, very good. This is the input that is in the Laplace domain, correct? So I have to know what the input is because I can't calculate steady state error unless I know what I'm providing for an input. And if I know GC and GP, I'm good to go. I got what I need. Okay. Well, before we can do that, we have to define this term. So we're going to define an open loop transfer function. And when you think closed loop, right, we go all around the path. Open loop means stop right there. Don't actually close the loop. So if I wanted to get the gain right to this point, if I wanted to get, we'll call this, I don't know, we'll call this not C of S, but we'll call it EET for lack of a better expression. We'll call that EET of S. How do I get a transfer function for EET of S? That's just my input times these two feed forward paths, right? Stopping right here, that's R, GC, GP. So if I wanted to do a transfer function of output over input, that's just GC, GP. This here is really important to us because it really tells us a lot about the characteristics. This is the open loop gain of our block diagram. And it's essentially open loop because this here is not connected. That's why we call it open loop. The loop is not closed, it is open loop. So if we define our open loop gain or transfer function equal here, we know that when we multiply those out, we're going to have a numerator and a denominator, and those are both going to be functions of S. If we can factor out our S term here, so let's just say that we have S, at least one value of S is multiplied by all the coefficients, then we can factor that out front. This term N tells us the number of S's that we can factor out of our system. And that's so important, we're going to call that N the system type. So if you have a type 0 system, how many S's can you factor out? None, because it's 0. Because S to the 0 is equal to 1, isn't it? So I can't factor any of those out. So I'm just multiplying by 1, right? I can put any coefficient and multiply our polynomial and then multiply it by 1, and it doesn't change anything. So a type 0 system, whoops, has no S terms, right? A type 1 is S to the 1, which means in my denominator, it's going to be 1 over S. A type 2 system is S squared, which means in the numerator, in the denominator, you're going to have a 1 over S squared. What is dividing by S equal to in the Laplace domain? Taking an integral. This is equivalent to integration. Now, let's think for a second. If I have error in my system, right? Does an integrator help or hurt the error? Remember what is an integrator doing? What is the base definition of an integrator? Go back to your Calc 2 class. What is an integral doing? Calculates the area under the curve, right? So, what's that? It would hurt? What did you say? Well, let's see. So if I have an error that's doing this, the output of the integrator, what is it going to do? It's kind of going to track that output, isn't it? Is it going to track it? Or if my error is like this, what is the output of the integrator going to do? It's going to ramp up like this until the error gets to 0. And then doesn't it flatten out? Because the area under this curve, there's area here, right? And at some point, if I've got an integrator, the output doesn't just stay like that. Let's see if I can change the pen color. The output will start to drop until it reaches 0. Because when I integrate with no error, there's no more change in integral. So if I have a step input like that, or not a step input, if I have an error that's going along forever, there's nothing I can do. But then when I put an integrator, it has the ability, in some cases, to go ahead and look at the error and then try to get closer and closer to that's no error. Why is it proportional plus integral control? Because you have a DC or a fixed input, and then the integrator is trying to get rid of the error between that fixed input and the output. So adding the integrator means you have you could eventually get no error for a step input. If it's not a step input, then it changes things a little bit, it gets more difficult. But if it's a step input, we can go to error. That's why, and I think, did we talk about PI controls in Jude's class? I think you all said she doesn't cover proportional integral control. Okay, so when you talk about controller types in industry, there's P, PI, and PID, proportional integral, and derivative. And the most common of the two is proportional and integral, because that's the one that you can go ahead and potentially get 0 error. A proportional only, the way that that works is you always have to have error for the system to be able to output. So if there's no error, K times 0 is 0. And when you output something that's 0, eventually you're going to start introducing error, okay? So having or adding integrators in is actually a really good thing. And if you look up some of the terminology, they used to call them wind-up limits, or anti-wind-up limits, or reset limits, or all these different things. What's the bad thing about an integrator, mathematically speaking? It's just perfectly happy if the error is still doing this, right? If it's a rectangle, it's going to keep integrating until it gets to a really crazy high number. And so the problem with integrators is sometimes if your integrator is set too high, it goes to this really high number, and then your control system finally responds, and then you've got to bring the error back down all this way, and then you need a lot of error in the wrong direction, and so you end up kind of oscillating back and forth. And so you have these wind-up limits so that your integrator doesn't just go to this really crazy big number, it locks or stops at a certain value, okay? And you can take a look in most control systems books, they actually provide that capability. All right, so let's do math. And let's take a look at our steady state error. So our input here is a step input. Notice the U of t, that just means a unit step. If you remember from your Laplace table, a unit step input translates into 1 over s. And remember, we got to be careful because a unit step input also looks like 1 over s, where an integrator is 1 over s. But one is an input and one is the mathematical operation. So the transfer function, if it has 1 over s in it, means there's an integrator there. If the block diagram has a 1 over s, it's built into it's an integrator. But if I input it with a step input, that's the 1 over s that comes out front. That's the only time you'd see a 1 over s in the input stage cases when you have a DC or a step input. And we're just going to pick some random value, some unknown value of magnitude. It could be 1 volt, it could be 12 volts, it could be 5 million volts, et cetera, et cetera, et cetera. You just, the value of A is what it needs to be. All right, so let's go ahead and plug that into our generic steady state error calculator. So we just grab this from the before. Limit as s approaches 0, s times A over s, which again, this is equal to R of s. So we're going to put that right into here. And then we're going to divide that by 1 plus G sub C, G sub P. Now, this here, we want to rewrite it. This is A over S times S times 1 over 1 plus GC GP, correct? The S terms cancel out, don't they? So I'm over here. I'm at this point. This limit function is only dealing with as s approaches 0. What happens to a as s approaches 0? Nothing. The constant. A is not based on s at all. So who cares? Leave it alone. So a divided by s, when I multiply by s, just becomes a. And this here, I don't need to do the limit as s approaches 0. It has nothing to do with s, so I can write it on its own. The same thing with the 1. 1 is not dependent on the value of s approaching 0. So I can ignore it. This term right here, the open loop gain that I see over here, that is dependent on the value of s. So I'm going to move my limit function over to here. And now I'm going to define a term called k sub p. Anybody want to guess what the k sub p term stands for? It's the proportional constant. Okay, and we'll see why we talk about k sub p, and we'll define the terms and see if you can get what the next one is. So now my steady state error is going to be a, whatever the magnitude is of the unit step that you provide, divided by 1 plus k sub p, where k sub p is the limit as a limit as g sub c, g sub p, etc., etc. Okay. So proportional, some people say position. We'll do either one. If the system is a type 0 system, then ESS is 1 plus k sub p. What if it's a type 2 system? Or a type 1, type 1 system? What's a type 1 system? A over, keep going. You sure there's the S? It's going to be 1 plus S times GCGP, right? Because we factored out, actually it's not GCGP. There's an S because this is 1, isn't it? Right? What happens when we take the limit as S approaches 0, this system? This is 0 times something. What is 0 times something going to be equal to? 0. This just becomes A over 1, does it not? But this term right here, which we defined as k sub p, is going to blow to infinity. And my steady state error is going to be equal to A over 1. Why do I have 0 here? Let's see. I'm gonna bring up whiteboard. I'll do up the maths so we can see it all. So we'll look at the transfer function again. We'll go back to the base transfer function that starts. Hold on, keep going. There we go. All right, so we had our transfer function was equal to GC GP over 1 plus GC GP, correct? And a type 1 system means we have at least 1 over S here. So actually Noah was right. We should have a 1 over S out front of the whole thing, correct? Not just on that term. So that was incorrect. So this here should be A over S times 1 plus GC GP, correct? And if we take the limit as S approaches 0, that whole denominator term goes to 0, correct? So that means ESS is going to approach infinity. Okay? So if we have a type 1 system, which means our input is not ESS, not 0. It's let's see. So it's 1 A. Why am I having a hard time with this? So it's A over 1 plus K sub P, which is equal to A over 1 plus the limit as S approaches 0, S times GC GP. So my K sub P term is going to be equal to the limit as S approaches 0, S times GC GP, which means that's going to be equal to 0. Am I getting infinity? Let me think for a second. Oh, I get it. Sorry. No, it's 1 over S, right? We have an S in the denominator, not in the numerator, because an integrator would be 1 over S. So this is 1 over S, which means that term is infinity, not 0. So A over 1 plus infinity, what's that going to be equal to? 0. That's equal to 0. Yeah, so the problem is when I do my, when it's a type 1 system, I should have GC GP is going to be equal to 1 over S times a numerator and a denominator. So when I take the limit as S approaches 0 of 1 over S times that, that's when 1 over S, the S term goes to 0, but the 1 over S term goes to infinity. Say that again. Well, this is the K sub P term. There is no A. That's only when I'm calculating the steady state error. The A term comes about, remember, from R of S is equal to A over S. Right? So in the denominator, I mean, in the numerator, there's no A term. It's only when we add in the input. So sorry about that. So this should be 1 over S there. So anyway, with a type 0 system, we have to get some steady state error. That's A over 1 plus K sub P. For a type 1 system, our K sub P term is going to be equal to infinity, and our steady state error is going to approach 0, which kind of makes sense. Do you remember how we talked about a unit step input? So if we have a unit step input here, if we don't have an error, if we just have a proportional only controller, what ends up happening is our output is going to do something like this. And that error is going to be constant. Right? So this is the output. And that is the error. If I add an integrator, so this is the error, you know, the nominal error if it was allowed to persist forever. Over here, I have this value. Now I'm going to ramp up, and at some point, my output is going to match what the error signal would be, and then it drops away. So this would be proportional only. And this would be proportional plus integral, right? So by adding that integrated to our system, we've actually gone ahead and made it so that we get no steady state error. So again, think about it in terms of industry, proportional and integral controller. If we're trying to maintain the tank level at 30%, we can get the tank level to 30% if we add an integral. If we don't add an integral part to our controller, then we're always going to have some sort of steady state error. Usually not. Why would there not be overshoot? Because this is the error before, right? This is the sort of the pre-error. What actually happens to the error? I guess I'll change it to purple. The error is actually going to start to do this, right? It's going to drop until it gets to 0 and then goes here, doesn't it?
Yeah.
Like this slope here, you know, it's not continually increasing at a constant value. It's actually dropping down. Why? Because the error here, the area under the curve here, is way greater than the area under the curve here. So it's slowly bringing it in to the desired value. Okay. And these are steady state errors. That doesn't mean they're fast response. It just means that it's going to get to a value that's reasonable. It just might take a really long time to do that. Good question. So if it's a type 1 system, no steady state error. How about if I had 2 integrators? What if I had a type 2? Then K sub P is going to be the limit as S approaches 0, ... This is S squared, ... Does anything change? It's still going to be the limit as S approaches 0. You've got 2 S's at 0. So if both of those are going to 0, you're still going to get 1 over 0, which gives me infinity. So my steady state error is going to approach at 0. So that's why anything type 1 or greater for a step input is going to result in no steady state error. Okay. All right, let's go to a ramp input. And a ramp input is going to change things just slightly. Not a huge deal, but we'll see how we'll have to modify that K term, or not the K term, but the ESS expression just a little bit. All right, so ramp input is A. The only difference now we have is a T term there, right? It's still going to have a unit step multiplier because we want it to start timing at time t equals 0. We don't want it to start, you know, at some random time. We'll start it at time t equals 0 to make our work a little bit simpler. And this in the Laplace domain is just A over S squared. Now I'm going to stick that into my generic ESS calculation. And what I end up with is limit as S approaches 0, S times AS squared over 1 plus GC GP. As I did before, I'm going to cancel out my S terms. So this one cancels out, but only one of these goes away, right? So the S that I need for the final value theorem only cancels out one of the integrators. Not one of the integrators. One of the S terms that are going onto the input. So now I have A, and I have to multiply. So I move my S down over here. And I'm going to multiply the entire denominator by S. Before, I only multiplied by 1, right? Because these two canceled each other out. So that was multiplication by 1. So we had the 1 plus the limit expression. Over here, we have an S over here and an S over here because we distribute the S term. A is not dependent on S in any way, shape, or form. So as S approaches 0, doesn't matter, doesn't care. Goodbye. What about that first S term as the limit approaches 0? What happens to that? What happens to that S term? Right, because I can break this up into this. This is just the denominator. Correct? The first one goes away. It goes to 0, right? So I can ignore it. It's not going to affect anything. It just goes to 0. So all I have left is that second term. So in my final expression for my steady state error for a ramp input, I have A over the limit as S approaches 0, S times GC GP. And just like we did before, where we define K sub P, now I'm going to define K sub B. So K sub B is going to be equal to the limit as S approaches 0. Let's move that down over here. So that's going to be equal to or S GC GP. Before I call this K sub P, position or proportional constant. What do you think K sub B stands for? Volatile? Look what you're doing. Remember what K sub P was. That was the limit as S approaches 0, GC GP, correct? What's the difference between K sub P and K sub B? The extra S term. What does the extra S term do? Not yet, just mathematically, like in general. What does the extra S term do? What's that?
Oh.
No, I don't think so. We talked about this all the time last semester. What is the mathematical operation of multiplying by S equivalent to in the time domain? Taking the derivative. If I take the derivative of position, what do I get? And how do you say rate of change? Another term. Slope, okay. Keep going. Rise over run. Anything else?
Speed.
What's another way to say speed?
Going back.
Velocity. Starts with a V, right? It's the velocity of whatever it is. Velocity is a more generic term, right? At least from physics. So velocity. So that's why, and there really is no, somebody back in control systems, they said, hey, let's call this K sub P. And well, we're taking the derivative of this, right? Multiplying by S. Derivative of position is velocity. So that was just a Q. If you can kind of keep that back, the base one is K sub P. That's the limit as S approaches 0, GC, GP. If I take the derivative of K sub P in the time domain, that's the same thing as saying this, correct? S times K sub P, which is K sub B. So I just gave you a little bit of a clue for learning this material. If you can't remember, because you're going to have 3 of these, if you can't remember, just remember the one. Burn it in your brain. K sub P is the limit as S approaches 0, GC times GP. Velocity is the first derivative of position in the Laplace domain. I just need to multiply that by S. All right. So that's, go ahead.
Where do you accelerate?
What do you know? He's jumping ahead, isn't he? Trying to zoom ahead of me. I think you might be right, but let's walk before we can run. Let's finish our velocity stuff and see if we get to acceleration. So we define that velocity. If it's a type 0 system, then what happens? Well, type 0 systems, how many S's do we have? How many integrators do we have, or what's the type system? That means we have A over S, and then our transfer function is here, but we have 1 over S to the 0 here, right? That's what a type 0 system is, which means that's 1 over S. So we end up with A over S times whatever our block diagram is. When we take the limit as S approaches 0, let me write that over here, the limit as S approaches 0, what happens here? It's really not that A term. It's really, let me get rid of the A term up here. Is that the error? What happens to the limit as S approaches 0, S times whatever? Goes to 0, doesn't it? Because we can't get rid of, we don't have any integrators in the system. So that S term that we have to multiply through because of the ramp input doesn't go away. And because of that, our velocity constant goes to 0. And when we plug that into our steady state error final calculation, notice the one term now is gone, right? So in the case of P calculation, or the error, the steady state error for a unit step input, we actually had to include the 1. For a ramp input, we only do A over K sub B, and A over 0 is equal to infinity. So it's not A over 1, it's A over 0. So this is equal to infinity. That's type 1, type 0. Let's move to a type 1 system. Now, that type 1 means we have one integrator at S, or one pole at S equals 0, one integrator, and the S terms will cancel out. So the S terms cancel out. So now my K sub B term is going to be equal to the limit as S approaches 0, whatever the numerator is and whatever the denominator is. And that's going to be a number, whatever number that is going to be our KV. And then our steady state error is going to be A divided by K sub B. So what this tells me, if I have a type 0 system and I hit it with a ramp input, I got no chance of keeping up with the output. So if it's so this is for a step input. For a ramp input, my input is doing this, right? It's ramping up like that. For a type 1 system, let's change the color. Come on, I am selecting it again. Okay. Oops. Let's pick yellow. For a type 1 system, actually, let's go back to this. This is the input. Now let's go for a type 1. Or type 0, I should say. What ends up happening is my output is going to do this. It's going to kind of stabilize out, right? It's just going to go to a flat value. So I didn't draw that very accurately. Let me see if I can draw that a little bit nicer. Anybody know how to change this thing so that it's not 45 degrees? I just have to rotate it by hand. Okay. So it's going to ramp up to some value. I can get this even Steven here. And then it's going to flatten out. So this error keeps increasing, doesn't it? It just gets bigger and bigger and bigger. So if you allow time to approach infinity, then it just becomes infinite error. Now, if I go to my next input, which is a type 1 system, let's pick blue. Type 1 system is going to kind of maybe start off about here, but eventually it's going to track the input pretty closely. So the error between here is going to be a constant value. This error over here is A over K sub B for a type 1 system. Let's go back and go for a type 2 system. So a type 2 system, I only will cancel out one of the integrators that's in our original block diagram. So the S here in the denominator, as that approaches 0, becomes 0 in the denominator, but then becomes infinity when you invert it. So 1 over 0 or A over 0, whatever the term is going to be equal to infinity. And then when I plug that into here, A divided by 0 is going to equal infinity. So for a type 2, or greater system, you'll have a little bit of error at first, but then it tracks it perfectly. So you have no error, no steady state error. So if you want to hit something with a ramp input, then you need at least 2 integrators in your system. In the real world, you don't often see type 2 or the need for type 2 systems. Why is that? How many of you are designing systems where cameras are ramping along and trying to follow a car or something like that? Maybe you've worked in Hollywood, or maybe you've worked in defense, missile defense, where you're trying to track the trajectory of a missile or something like that. Yes, that would be the case where you were actually doing that. But most of the time in the process control world, we want our output to be 30%. Much more simple, much less stressful. So that's why we don't have proportional plus integral controllers in standard industrial control. It's proportional plus integral only. Okay, so type 2 or greater, you're going to have 0 error. And the last case is if we have a parabolic input. So parabolic input is kind of the wackiest of the bunch. So let's do here. And this is a parabolic. So parabolic does this, right? It's t squared. So this r is equal to t squared. So that's my input, ramping up at a crazy value. We already have a pretty good idea that a type 0 system ain't going to do much for us, right? So it's going to kind of ramp up and then go here. A type 1 system. I don't know why it went bigger, but type 1 system, kind of going to do the same. How did I pick blue? Why is that coming up? Oh, because yellow and blue make green. Man, whiteboard is pretty fancy, right? You're not impressed? I'm impressed. That ramps like that. Again, the errors, nobody's impressed. Yellow and blue make green. Somebody was pretty creative, right? I would have just not mixed them. I would have just said, hey, just right on top of them. It's actually kind of a drag that they actually changed the color to green, because if you're trying to, I'm not mixing 2 paints together. I'm just trying to show lines on top of each other, but to each his own. What's that? It's a little impressive if you're an artist, I guess, but if you're trying to do engineering stuff, maybe there's a mode that we can switch it to. No, definitely not. So this is a type 1. And I forgot to put the color for type 0. And our next system, we'll call it, is our type 2. And that's going to track it pretty closely, but it's going to have a constant error at the end. So let's see if that's what we end up getting. So parabolic input. The only thing is we have a t squared there. That translates into an s cubed term. We plug that into our generic term, and we see that this s cancels one of the s's for the input. We distribute that s squared into this. So we have s squared. This should be, there's a typo here. This should be s squared up front. Let me see if I can change that real quick. Sorry about that. So this should be, we got to put another parenthesis in here. And if everybody knows, if you're using equation editor, there's a difference between built-in parentheses and the parentheses over here. You want to use these parentheses because they'll resize as necessary. So that's 1 plus that. You'll see it'll actually resize here. See, the parentheses got a little bit bigger. So it ends up resizing a little bit. Let me move this up just a wee bit. Move this up. Close enough. Let's go back to here. Switch. So then we have our S squared that's distributed here, right? And we know that as the limit as S approaches 0, doesn't matter. So this one can go in the trash. It doesn't mean anything. All we're left with is this. Noah, when you multiply K sub P times S squared, what do you think you might get? Yeah. You take the second derivative of position, you get acceleration. So why do we call that acceleration? Because it's S squared times KP. Remember, you only need to memorize the equation for KP, and then you take the first or the second derivative, get the velocity and the acceleration. Okay, that's all you need to do. Yes, sir. If it's the input's T cubed, so that would be another one. And you would have to just go with a higher level type system. You need more integrators to make the system work. Yeah, it does impact it. You just have to keep adding integrators. Oftentimes, we don't go any higher than the K sub A term. But you can. Does anybody here into RC cars? Many years ago, we had a student that was really into RC cars. And I was like, well, how fast does it go? Oh, that's not the only thing you need to know. You need to know how it accelerates. You know, acceleration is more important. And then how fast something can accelerate is another term. That's called jerk. So you can actually define another characteristic, but I've never seen it in control systems, which is the jerk characteristic of RC cars, which is not how fast the velocity changes, but how fast the acceleration changes. So you're taking the third derivative of the system. So if you needed to go to the next input, which I don't even know what the T cubed would be. T squared is parabolic. T cubed would be, mathematically, I don't even know if there's an expression. Does anybody know what T cubed is? You have step, ramp, parabolic. What's beyond that? I don't know. What's that? It shouldn't be squirrely. It would just ramp up faster, right? But I don't think it'll cut back on itself. It should still continue to increase, but it just looks like a parabolic, but at a faster rate, I'm guessing. I don't know. If you did T to the 5, I think no matter what, and you can correct me if I'm wrong, but if we, well, we do this, that's T, right? Oh, no, that's 1. That's T, so this is 1. This is T squared, and then T cubed. And I would imagine it would just be on and on and on, right? It never goes to the left. It always goes to the right because it just gets big so fast you can't really see it. So eventually it would almost be a straight line going up, right? Like you really wouldn't be able to see any. So it would almost look like it's, you know, a really high value, but I don't know. I've never seen more than T squared. So it's a cubic function. Okay. Yeah. So we have Ka, which is our S squared, GC, GP. Thanks to Noah for picking that up. That's acceleration. If it's less than a type 1 system means, or type 1 or less, this is going to be 1 or less, right? So I'm not going to cancel out all the S terms that are multiplied here. I have at least one S term is there. When I take the limit as S approaches 0, that's going to be equal to 0. So in all systems, type 1 or less, my Ka is going to be 0, and my steady state error is going to be infinity, as we've shown here, right? For parabolic, we could see for type 0, type 1, and type 2. Type 0, type 1, the error just keeps getting worse and worse and worse. And type 2, it tracks it pretty well. It doesn't get on top of it, but it tracks it pretty well. So let's move to a type 2 system. the S's will cancel, and I can get an actual number for K sub A. I don't get infinity or zero. So this is going to be a constant. It's going to be a value that is different between I'll put the final value in there. Okay. And then for a type 3 system, now I have S squared over or multiplied by, not over, an S cubed term. That goes away, but not all the S terms in the denominator go away. So when I take the limit of that as that approaches 0, that goes to 0. So my Ka term becomes something over 0, which goes to infinity, and my steady state error goes to 0. Okay. So in summary, we can build a table, right? And we can do system input. So we have a step, parabolic, and a, not parabolic, ramp, then parabolic. Then parabolic, right? And then we have the system type. We have type 0, 1, and we'll just stop at 2, right? So these are the system types. So if it's a type 0 system, my K sub P is going to be equal to whatever the magnitude is over, no, that's steady state error, sorry. My K sub P is going to be the limit as S approaches 0, GC, GP. My steady state error is going to be equal to A over 1 plus K P. Let's move these down a little bit so I have some room. That's for my step input for type 0 system. For type 1, no calculations necessary. And for type 2, that's for a step. For a ramp, I'm not even going to bother calculating K sub P. I know that K sub P, what's K sub P going to be equal to? 0, right? And ESS is going to be equal to infinity. Over here, now I'm calculating KV. Let me zoom in a little bit so I can give myself some room. K sub V is equal to the limit as S approaches 0, S, GC, GP. And my steady state error is going to be equal to A over K sub B. For type 2 system, K sub B is going to be equal to infinity, and ESS is going to be equal to 0. For parabolic, this is really easy, right? K sub B equals 0, ESS is equal to infinity. My K sub A now is limit S approaches 0, S squared GC times GP. And my ESS is A over K sub A. The only thing you need to remember is K sub P is the limit as S approaches 0, GC, GP. Then KA, K, not A, KV, is S times K sub P, and KA. So when you do these problems, when you're doing the homework, you need to identify what's the input, then you go to that row. Then what's the system type, and then you hone in over there. If it's a type 0 system, for a step input, you do your calculations here. If it's a ramp and it's a type 0 system, you have no calculations to do. You can just go ahead and specify it. So use this table, write it down, use this table, go ahead. And when you do your homework, when you do tests, you do all that stuff. And if you look at, anybody here have the FE review manual? What do they call it? The study guide, not the study guide, but the actual, the handbook. I guess I would like to show it to you, but I can't run Edge because it seems like the computer. So FE electrical handbook. Oh no, I don't know if I have one of those. Whoop, what happened? Let's see, maybe Mississippi State has it accessible. I just want to look at it. I just want to see the control systems. All right. So I don't know. Is it 471 pages?
Yeah.
Oh wow, let's change then. It used to be in the old manual, you had 70 pages or whatever. You could find it really easy. So this is brand new. Nope, no, you did an electrical one and they just gave you one book instead of having, 500 pages. This is absurd. Let me just see if I can go to the electrical section. 417 is the electrical section. Okay, perfect. Let's see, you guys are good. Wakes up. Come on. Might not be able to wake it up, but if you look in here, they do have, if it ever wakes up. Here we go. That's 417. What happened? I don't think it's under the systems engineering. I think it's under. Here, let's do this. Instead of going to that one, that's crazy. Let me just look for the electrical one. I don't want the new one. But sometimes they keep it someplace else, so I don't dare go to Reddit because that's a dangerous spot.
Google results.
Yeah,
It's not good.
There's always bar. I thought they showed it ago. No, I thought it was Internet Explorer that now. There was Internet Explorer with it. Yeah.
Well, maybe for the next class, I'll be able to have it, so I'll try Google. FE electrical. Okay, I don't want that. It's giving me the same, I did Google, didn't I?
Maybe you wrong. You painted Google.
I binged Google.
Yeah.
Let's see. Will this still have the electrical one available, or do they kill it? I don't know if I have a. I don't have one.
Yeah, man. Yeah. I think I don't. You don't, or- I think I don't.
No, I don't want that. I just want the FE handbook, the free one. If I can't find it here, I will give up, but you can take a look. So in the FE one, without the 500-page one, there is a way. Let me do this. Let's do a NCES FE review for steady state error. I know that. I just want control systems and FE electrical.
Not bad.
This kind of looks like it's here. And this might have been just a copy, but I can't find it, but it is in there. And that table that we developed here is pretty much the table that you would see, but they don't use case of P, case of B, case of A. They just call it K. At least that's what they used to call it. So the only reason why I told you about case of P, case of B, and case of A is because that little, you know, kind of helpful reminder how to get the other two. As long as you memorize one, you get the other two. Any questions? I think I'm out of time, or just about out of time. All right, so don't forget, on Thursday, we'll do an FE review. The following Tuesday, if you have any last minute questions, we'll go from that, but then we'll have a test. So we really won't get too much into this material until, right? We might get a little bit more on Tuesday, a week from today, but our next class will be pretty much focused on just doing exam review. We'll go from there. All right, folks, have a great day. See you all later.